you everyone for coming to our third climate snack. We had first Josh Fisher and then Asmerit, and now I have the pleasure to have Rob Jackson here. I don't think Rob Jackson needs a lot of introduction, but Rob Jackson is a professor in the Earth System Science Department at Stanford, senior fellow at Stanford's Wood Institute for the Environment, and chair of the Global Carbon Project, among other positions and appointments. Over time, Rob has accumulated more than 100,000 citations with a total H index of 141. So he's truly a rockstar scientist, but he's even better supervisor and a mentor. So I've been very lucky to count Rob as my supervisor and mentor at Stanford and beyond. And he's made a huge impact in lots of young scientists like myself. Also, Rob doesn't give a lot of seminars, so it's truly an honor to have Rob here today with us. He would talk for about 35, 40 minutes, going through his slides, and then he will answer some questions at the end. So please use the chat box if you have questions, or raise your hand at the end of his presentation. So thanks, Rob, and yeah, the stage is yours.
Thank you so much, Cesar. It's a pleasure to be here, and thank you all for coming. As he mentioned, we'll try and be pretty brief and save lots of time for questions at the end. And I won't be able to monitor the chat box as we go along. So if there's something you're dying to ask, you can feel free to jump in, but we'll come back to them and work our way through the questions. So let me share my screen and we'll get started. Are you seeing presenter view or full view?
Yeah, that's good. It's perfect.
That's good. Okay. Well, thanks again. Cesar asked me to talk a little bit about our work, kind of mixing a bit of ecology and climate change. And I'm going to talk specifically about methane today, what the opportunities are, what the largest sources are, and how we can reduce methane emissions. It will we'll take sort of a global view at the beginning of the methane cycle, where methane comes from, where it has changed the most, and then we'll look at some of the ways to measure and reduce those emissions. So energy, climate, and methane mitigation. Thanks again for coming. I want to start by acknowledging the Global Carbon Project. My colleagues like Pep Canadell and many others, I'll acknowledge them as we go through the talk. And I want to highlight that most of you may know this, or some of you, but in 2020, was the first year we were able to present global updates for all three major greenhouse gases: carbon dioxide, methane, and nitrous oxide. Carbon dioxide led by Pierre Friedlichstein, methane, the methane budget led by Marielle Saunois in France, and then nitrous oxide led by Hanshin Tian and Rona Thompson. So thank you to them and their colossal work. And all of this information is publicly available, and including the slides and other things. So I'd encourage you to look at the GCP website, just globalcarbonproject.org. GCP, we also, along with the budgets for greenhouse gases, we study urban, regional, cumulative, and also negative emissions. And we're a completely open organization. Anybody who wants to contribute is welcome to do so, and we love to have as many collaborators as possible. Well, let's dig into methane then for a bit. And I think all of you have seen a typical trace. This is like the Keeling curve, but for methane, looking at how methane concentrations have risen, in this case, over the last 40 or so years. And you see that there was a period of rapid growth for a couple decades, a relative stasis around the turn of the millennium, 2000 to 2006, where methane concentrations were flat in the atmosphere for reasons, to be perfectly honest, that the scientific community has never explained fully and still debate, which is a little bit embarrassing. And then starting around 2007, concentrations began to jump, and they rose steadily. In the last 2 years, we've seen the biggest increases on record. 2020 saw a 15.7 parts per billion increase. And then 2021, the preliminary data from Copernicus in the EU suggests a 16 part per billion increase. So those numbers are deeply troubling, because the last thing we need is for methane concentrations in the atmosphere to start going up in an accelerating fashion. Going up is bad enough historically, but I want to credit NOAA, Ed's work, and then the EU folks with Copernicus. So that's the backdrop, if you will, to what's happening in the atmosphere, and things seem to be rising very rapidly. Methane is also the second most important greenhouse gas after carbon dioxide for trace gases under human control. It's contributed 2/3 as much warming as carbon dioxide since the late 1800s. It's also more potent than carbon dioxide ton for ton, and shorter lived as well. So it's far more potent when it's in the air, but it goes away more quickly than carbon dioxide. This is a figure from the brand new IPCC, the AR6 working group 1 summary. And the red bars show the temperature change attributable to different forcing factors. Carbon dioxide's on the left, shows about a 3/4 degree C increase in the average for the decade of the 2010s compared to the late 1800s. And the increase attributable to methane is about 1/2 degree. Now that doesn't mean that the temperatures went up 1/2 degree attributable to methane in the 2010s. It means that when you look at the global climate over that period and compare it back to a century or so, you see the methane contributed about 1/2 degree. So that means, methane's not as strong a forcer as carbon dioxide, but second most powerful and really something that's of concern. Methane is also, because of its shorter lifetime and its potency, in some ways the best lever that we have to try and delay peak temperatures and shave off peak temperatures too. So that's why there's been so much attention placed on methane in the last 6 months or so. You saw and all heard about the global methane pledge that was launched during the COP in Glasgow between the US and the EU. More than 100 nations now around the world have pledged to reduce methane emissions 30% by 2030 or so. That's nice to see. And it's nice to see a lot more emphasis being placed on reducing methane emissions as a complement to tackling carbon dioxide, which is still the most important greenhouse gas. Well, in terms of how much weight to assign methane, this is a recent paper that a grad student in our lab, Sam Abernethy, just published last week in Environmental Research Letters. And there's a lot of sort of controversy, or perhaps disagreement is a better word, about what global warming potential to assign to methane. The most commonly used metric is a 100-year time frame, and in that case, methane's about 30 times more powerful than carbon dioxide ton for ton. But if you look at a 20-year time frame, which is also used pretty widely around the world, it's more like 80 to 90-fold more potent than carbon dioxide for its global warming potential ton for ton. So this is a nice piece of work that Sam just published, and it takes into account the potency of methane and also the sort of the exponential decay, if you will, through time. Methane's half-life is only about 12 years in the atmosphere. So the closer your temperature threshold is to you, so 1.5 C threshold will be passed in a couple of decades if it's passed. And so the shorter term, the deadline is, if you will, the more important and more effective methane mitigation is. So in this analysis, we calculated global warming potentials with specific temperature thresholds in mind. And our analysis suggests that if you care about 1.5 C, as the Biden administration has as its target, the GWP to be used for methane should be about 75, which corresponds to about a 24-year period from now in the models. So that's close to the 2-decade value that's used around 80. But if you're interested, this paper presents temperature justified, if you will, global warming potentials for methane. Either way, we're undervaluing methane. The EPA's global warming potential is about 25, so 1/3 of our recommended value, and less than 1/3 of the 20-year time frame. And that value is out of step with the Biden administration's explicit goal of 1.5 C stabilization. So we'll come back to that maybe in the question and answer session. EPA uses the UNFCCC 100-year metric, so that there is some justification for what they do to be consistent across countries. Well, let me present a few slides from the global methane budget just as background. Credit again Marielle Sonnois and Philippe Bousquet, past leaders of the global methane budget. And I think, as most of you know, more than half of methane emissions around the world are now coming from human activities. Roughly 2/3 of those are agricultural and 1/3 arising from fossil sources. So anything that's orange arrow pointing upwards on this figure is a source from anthropogenic activities. On the far left is fossil fuels. So that's coal, oil, and gas. That's about 100 million tons a year. Agriculture is a couple 100 million tons a year. That's the second bar from the left, the thick bar in orange. The largest natural source of methane to the atmosphere is wetlands in green, shown here about 190 million tons a year. And there's a little that comes from biomass burning that's both green and orange because some fires are quote unquote natural and some are set by people. The bars on the right deal with the sinks. So these are the processes that destroy methane in the atmosphere. And that's scrubbing from OH and chlorine radicals, and then soil microbial uptake on the far right. So it's sort of the atmospheric cleansing mechanism is the most important process for eliminating methane. And it's also important to remember that all the methane that we release into the atmosphere, when it's oxidized, its ultimate fate is as carbon dioxide. So it turns into CO2 in the air. So we're going to look today at wetlands and agriculture briefly, and then focus in on fossil fuel sources. That's kind of our outline for today. So I'll start just with a few slides on wetlands and where different sources are coming from. So it's a slide also from Ariel's paper a year or two ago. And these are based on inventories, things like the EDGAR inventory. And these are pixel-based estimates of where methane emissions arise from. You see wetlands in the upper left. The darker the red, the larger the source per area and time. Agriculture and waste below that, correspondingly, not surprisingly, with the kind of the agricultural breadbaskets of the world and high population areas. And then fossil fuels in the upper right. So while the resolution on these pixels isn't enough in this data set to understand, every specific source that might be large, it gives us a pretty good idea of where to look for methane around the world. So let's start by taking a look at wetlands and what's happening there. There's a lot of work already underway trying to understand whether climate change may already be increasing natural sources of wetlands. So it isn't just human sources from agriculture and fossil fuels that we need to be concerned about. If climate change increases temperatures and if hydrology were to stay the same, we would expect methane emissions to increase in natural wetlands because of that rising temperature. And then another major source of concern, of course, is permafrost thawing. And if permafrost thaws, and you start to see an acceleration in permafrost thawing, then the thousands of years of carbon that's stored in that permafrost much of it will likely come off either as carbon dioxide or methane. And the balance of carbon dioxide to methane depends on local hydrology and waterlogging. There's a lot of concern about the potential for runaway methane emissions in permafrost, a lot of news coverage of kind of bubbling water and thermokarst in places like Siberia, but regionally, at least globally, we don't see evidence for rapid acceleration of Arctic emissions. Arctic methane emissions are still quite small, but there is some evidence, especially in the tropics, for rising methane emissions in tropical wetlands. I'll point in particular to a symposium that Ewan Nisbet and Anna Jones organized last fall for the Royal Society in the UK. And they've done some really great work in Africa in particular, documenting methane emissions. A lot of good satellite work going on there too. So I'll point you to their website, Rising Methane is Warming, Feeding Warming. As part of the Global Carbon Project, our lab recently established a new public methane FluxNet database. This site is open to the public. We have methane flux data over multiple years at almost 100 sites, and we're continuing to build this site. Some of the postdocs who worked on the project are shown on the left. Kyle Delwish at top and Sarah Knox, not shown, but helped kick this off too. She's at UBC now. The plot in the middle shows the cross-site sensitivity of wetland methane fluxes to soil temperature. So we have soil temperature on the x-axis in degrees C, and then the methane flux in grams of methane carbon per square meter per year. And you see a very steep slope and a pretty tight relationship for methane fluxes as a function of soil temperature. This is not a climate change figure. This is a cross-site aggregation. So this is not the same as taking a single site and warming at that site. But there is clear evidence that as temperatures go up, both within sites and across sites, we expect methane emissions to increase. I'll point you to a couple of papers in the lower right, Sarah Knox's, Kyle Dewish's, and Jeremy Irvin's in our AI for Climate effort. You see the sites in the lower left in this figure, and we're in the process now of trying to build out new sites in the tropics as part of our new effort. So methane emissions from wetlands are large. They're the largest natural source. They may be increasing, and we need to keep monitoring them. The largest human drive source is agriculture, and that may be a surprise to some people. More than 100 million tons a year of methane come from ruminants, and another 30 or so tons come from rice farming, waterlogged conditions. And I should say that methane is formed in low oxygen or no oxygen environments by microbes. So in that sense, a wetland is similar to a rice paddy, is similar to the gut of a cow, which is just sort of a low oxygen waterlogged environment. So cattle and ruminants, 100 million tons a year. What can we do? Well, there's demand side management, obviously. That's why there are calls to eat less red meat. So ruminants include cows, goats, and sheep, for instance. There's a lot of emphasis today on plant-based foods and such. We can also reduce food waste because as food waste stacks up, it acts like an incubator, and methane is often formed in these systems, especially in wetlands. I'm sorry, in landfills and other places. There's a lot of emphasis on using feed supplements such as algae or essential oils. So adding small amounts, and by small, I mean really small, like 0.5% or less of feed, has been shown to reduce cow emissions of methane by 80 to 90%. There's good work going on here in Australia. The best work that I'm familiar with here in the United States is at UC Davis, people like Frank Mittelhofer and Armias Cabrabe. Pardon the pronunciations of their names, but there are a lot of studies showing substantial decreases in methane emissions with very small contributions of feed supplements. And the trick is how to get those feed supplements to 1.3 billion cows around the world, especially cows that aren't in feedlot type situations. And then management of manures is another way to reduce methane emissions at feedlots, and some dairies, the stacks of manure act as incubators, and lots of methane is generated from them. And then in rice farming, 30 million tons a year, there's work looking at drawing down water levels temporarily so we can change the hydrology briefly, and that can have a good effect on reducing methane emissions. We have to be careful not to increase nitrous oxide emissions and other things. But there's reason to be optimistic that we can reduce emissions from agriculture. No single approach is going to do the job. We need pretty much everything we have at our disposal. And regionally, Europe is the region that's done the most to reduce methane emissions since 2000. That from a recent paper that Ann Stavert led for the GCP. So let me spend most of the rest of the time talking about fossil fuel methane sources. That's where my group's done most of our work. And I want to acknowledge that we care about fossil fuels not just because of methane leaks, but because of carbon dioxide emissions. And this is a figure from our new carbon budget that's just coming out in GCP. And these show you global carbon dioxide emissions in billions of tons for the major fossil fuels, coal, oil, gas, and then cement production as an industry. And I think the sobering thing about this figure is, in spite of all of the great work that's been done to mitigate emissions, only for coal do we see any evidence of a peak in global carbon dioxide emissions associated with fossil use. So gas use has gone up steadily for 60 years and continues to rise. Oil use had been rising steadily until the COVID-19 knocked it back temporarily. And only for coal do we see a hint of a peak back around 2014 or so. At least I hope it's a peak. It's quite possible that this coming year, coal-based carbon dioxide emissions will be above that level again, but I hope not. So as we're thinking about all this work to reduce methane emissions, it's important not to lose sight of the carbon dioxide emissions that come simply from burning gas and fossil fuels in general. So let's look at some ways to reduce these emissions. Here are some tools that we've used. I'll go over these, including street level emissions, abandoned oil and gas wells, household appliances, and oil and gas wells too. So we'll start with streets. So this work goes back 5 or 6 years now. This was a paper led by Nathan Phillips at Boston University. And these studies, we produced the first publicly available maps of natural gas leaks in cities. This is like driving a lawnmower across city streets, up and back, over and across, literally block by block across cities. And in Boston, we mapped in the red line shown here are the roads driven. The gold spikes, if you will, are the sites of each individual natural gas leak that we mapped in a car. This is a car based with a Picaro analyzer in back. So you have a GPS and an anemometer that gives you wind direction, so what side of a street is leak likely to be on, and then a concentration of the locating the emission. It doesn't give you a flux or an emission source. This just gives you the location of those. So you see about 3,400 leaks that we mapped for Boston, 4 leaks per mile on average. The number one predictor in Boston was old cast iron piping. Some of the piping had been in place for a century or more. So ultimately, we want to use this information to get things changed or to improve things. Within a few days of when our paper came out, the mayor of Boston wrote a letter to the Public Utilities Department to step up scrutiny and referred specifically to the work. At this time, Congressman Markey, now Senator Ed Markey, wrote a letter to PHMSA, which is a Hazardous Materials Safety Administration, a federal agency, suggesting that we needed to reduce leaks from aging natural gas pipelines in Boston and elsewhere to conserve the resource. These leaks are a waste, to protect consumers for paying for gas they don't use, prevent emissions of greenhouse gases into the environment, and more rarely, to prevent explosions too, because each leak is a potential source of explosion, as rare as those events are. And then the good outcome in July of that year, Massachusetts passed a pipeline safety bill to accelerate natural gas replacements and faster cost recovery for companies. So now one thing I want to highlight in the presentation today are ways that we can use data to affect change and make the system safer and make the climate healthier and help climate as well. So we went on to map Washington, D.C. next, mapped 6,000 leaks there. The Washington Post did an app based on our data set. You can see on the right the cities, but similar outcome to Boston. The next year, the utilities launched the Project's Pipes program, which was a 40-year accelerated replacement program for DC. Again, people may not know, but the utilities are limited in how much they can charge to consumers and recover the cost for repairing and replacing pipes. They want to fix these leaks on an accelerated basis, and these programs allow them to charge a bit more, but to be able to recover those costs more quickly and be able to speed up the transformation of the system. And ultimately, these bills cost consumers less than $1 a month and reduce the amount of gas they pay for that's lost and unaccounted for, because we as ratepayers pay for the leaks that happen from these systems. So DC was a similar number of leaks as Boston, about 4 leaks per mile. We wanted to look at places where replacement programs had already been put into operation, and 2 cities were Cincinnati, Ohio, and Durham, North Carolina. And these were both cities where replacement programs had been completed or almost completed. And there we found 90 or 95% fewer leaks per mile than in Boston, DC, or Manhattan that we mapped as part of this paper led by Morgan Gallagher. You see Manhattan on the right here, and then Cincinnati in the middle of the figure, and you see the obvious reduction in density. We had about 1 leak for every 2 miles instead of 4 leaks per mile in Manhattan. So these programs really do make a difference, and they require partnerships between the utilities, the cities, and sometimes the state, and sometimes NGOs. So I guess kudos to the areas that have already put these into place and really made a difference over the recent decades. I want to discuss a little bit some approaches from the air. What can we see from the air, and how can we identify the largest emitters, what we call super emitters? And I'll come back at the end of the talk to acknowledge some of the great things happening with satellites in this space too. This was a study led by EDF and David Lyon in particular. As part of this study, we mapped methane emissions large emissions from 6 regions in the United States at more than 8,000 well pads and facilities. And these are helicopter-based FLIR cameras, so an infrared camera that allows you to film and image large hydrocarbon sources that are invisible to the naked eye. And I'll show you an example in a minute. So you see a flare in the lower left, that's in the Bakken, oil and gas wells from the Bakken in the lower right, and then a wastewater holding pond or water holding pond in the upper right. So let's look at an example of the kind of image you can see with these approaches. So here's a well pad. In this case, you see a couple tanks in the middle of the image. So you're coming in a helicopter, and you see in this case, a leak or an emission from the top of those tanks. And you see the road to the right, that house in the background. And this would be completely invisible if you drove by in a car or walked by. And you can imagine that plume, sort of changing direction, wafting across the house, if you will. And so this is the kind of thing that imaging technologies like this can help us see. It's still expensive to go out in an airplane or helicopter and do this, but nonetheless, it provides some resolution that can help us. So what do we find in that study? Well, across these 8,000 well pads, the percentage of sites with large emissions was about 1 in 25 nationally, about 4%. And I guess I use the analogy of a restaurant inspection, where from the air you can show up unannounced and just see randomly what's leaking, and in some cases who's leaking, and try and feed that information back and work to reduce those leaks. So it was only 1 in 100 sites in Wyoming in the Powder River, and 1 in 7 sites in the Bakken. And one thing we observed was that big sources were more than 3 times as likely in oil producing areas than in natural gas producing areas. And even in the same play, the Barnett in Texas, where you have both dry gas and wetter gas with oil and heavier condensates produced under the same sort of regulatory framework, same area. You had 1 in 5 of the well pads that produce oil emitted, compared to less than 1 in 100 of the dry gas sites. And this may be that there are more tanks, more vents, more equipment on the oil well pads. That's true. But it may also be that when you're producing oil and propane and butane, you don't care about the methane. That's a less valuable product. And then 90% of the more than 500 sources we found were from tank vents and hatches. So that it suggests that there are things that we can do in the way we monitor those. And there are also pressure release valves that are relevant too. So this is a way of imaging emissions and trying to identify large leaks quickly and get them reduced. I'll come back to this topic at the end of the talk. I want to turn back to cities now for a second, because I want to turn next to buildings and homes. And as a follow-up to the study I mentioned with Nathan in Boston, we did work that was led by Catherine McCain and Steve Wofsy's group at Harvard. And in this study, there were sensors outside the city to monitor the quality and the amount of methane in the air before it blew into Boston, and then sensors on the top of skyscrapers, like you see here in the upper left. At the time, that was the Prudential skyscraper. It's called something else. So we could use these monitoring stations to look at how much methane built up in the city over time. And what we found in Boston over the course of a year or so was that the estimated emission was about 18 or 19 grams of methane per square meter per year. Now that estimate was 2.5 times higher than the state inventory suggested it should be. So it was a lot higher than expected. And we estimated that about 2.5% of the methane moving through the pipelines and the infrastructure in the city was reaching the air. And that number was a lot higher than expected. We found that gas or thermogenic methane contributed 90% of the air, of the methane in air over Boston in winter, and only 60% in summer. It was the same amount through time, but in summer temperatures were higher and you had other biological sources from sewer gas and such. So most of the air in all seasons had methane in it that was coming predominantly from fossil infrastructure. It was thermogenic methane based on isotopes and such. So one of the questions that we asked at the end of the study was, where's all that extra methane coming from? We felt like we had a reasonable sense of what to expect from distribution lines, the pipelines and streets in the city, from refineries and industrial sources, and homes and buildings. were one possibility, what we call post-meter emissions. So how much methane is leaking from inside the appliances in our homes and the appliances in buildings. The figure here, I'm sorry, just shows the methane concentration, the change in methane parts per billion on the x-axis, and the change in ethane, the y-axis, and the blue line is what you would expect based on published data for the pipeline natural gas in Boston at that time, and the red line is what we found. And what this figure just shows is that the methane to ethane ratio, if you expect pipeline gas to be the dominant source over methane, you would expect the ratio of those two gases to be similar to the ratio in the pipeline gas. And that is in fact what we found, to sort of 90% or so. So we knew that the thermogenic and industrial gas was the source of this. Well, when you look at, and the slide's a little bit out of date. This is a paper that Anna Brandt led. Here is or was EPA's estimate for methane leakage along the supply chain. It's a few years old now, but you see in this percent leakage, a couple of percent of the methane leaked out in the drilling and fracturing stage, according to the EPA, about 0.4% during production, another couple of tenths of a percent during processing, and then about 0.7% to more than 0.5% during transportation and distribution. These are cross-state pipelines and even more importantly, distribution lines within streets and cities. But interestingly, at this time, the EPA did not include homes and buildings in their estimate, and even today only include those partially, which I'll come back to. The estimate at this time for total methane leakage from natural gas use was 1.5%. That number is certainly too low today, as there's a lot of data that have come out, especially upstream and in fields like the Permian, where the amounts are substantially higher than these estimates. So we have a lot of work to do to reduce emissions, but they're pretty evenly spread throughout the upstream and downstream parts of the chain. So let's look at homes and buildings a bit more. Some of the things we've been working on in the last couple of years are abandoned oil and gas wells, and then emissions from homes and buildings. So on the left is a tented abandoned oil and gas well in the Marcellus region. This was work led by Mary Kang. And then on the right, a grad student, Eric LaBelle and back, and an undergrad, Simone Spicer. On the right, measuring a on-demand water heater on the outside of a house, trying to collect up the methane emissions from these different appliances and understand how large they are. So here's an example for water heaters. This is a paper we published a couple of years ago in 2020, led by Eric. The lower figure shows you how you might go about, or how we went about measuring these emissions. And there were 4 periods of time that we needed to take into account. The orange thin slice is what we call steady state off emissions. This is a little small amount of methane that comes to the air all the time, 24 hours a day. And you might think of this as coming from loose fittings or couplings to the appliance. Then when the appliance kicks on, let's say in the case of a water heater, there's demand for hot water. There's a puff of gas that's unconsumed, and this puff is most intuitive on a stove. When you think of that slight delay between when you flip the burner switch and the flame actually comes on, well, that delay occurs with a water heater too. That's in blue here. The yellow or gold is the unburned methane, the uncombusted methane while the appliance is working. And the green, again, you have a puff when the appliance shuts off. So you have to integrate all of these things to understand the emissions, and you have to know how often people use their appliances. And so we went through about, in this case, 64 houses to measure these detailed estimates of methane emissions. And we had our own loggers that we put in houses to understand how often people turned water heaters on and off or used them. And then we had national statistics we used to extrapolate to. So based on our work, we found that tankless water, these sort of on-demand heaters, emitted about 2.4 kilograms of methane a year on average. And they emitted almost 1% of the gas that they consumed into the air as unburned methane. And for a tankless water heater, the largest source were these on-off pulses. The on-off pulses were larger than we expected them to be. So there was methane entering the atmosphere every time the burner was on in these appliances, but that wasn't the biggest source of methane to the atmosphere. For the more common large tank water heaters, or what we call storage heaters, they emitted about less methane, about 1.5 kilograms per year. and a smaller percentage, about 0.4% of the gas they consumed. And interestingly, it wasn't while they were on, but it was while they were off, particularly associated with pilot lights, that we documented the largest source. And it wasn't that the rates were highest at that time. It's just that most of the day, the water heaters are off, and this small source of methane to the atmosphere comes to dominate the signal because it's 23 hours a day, or whatever that number might be. Again, always important to integrate the methane with the carbon dioxide emissions. So even though tankless heaters generated less, they gave off more methane than the large storage tanks. They were more efficient in terms of gas usage, and so they gave off fewer carbon dioxide equivalents overall, in spite of leaking more methane to the air, because they gave off less carbon dioxide. So your tankless water heaters are still better from climate, based on our estimates, than the large tank water heaters. And that's primarily because those on-demand heaters aren't keeping, a large volume of water hot 24 hours a day for on-demand. They're heating that water instantaneously when we use it. Overall, we estimate that water heaters in the US emit about 82 gigograms of methane a year, and about 4% of all the gas that they consume. So both those numbers were a bit higher than previous estimates. So I'll turn to stoves, and we'll finish up here quickly. And this work came out just a couple weeks ago. We looked at methane emissions and indoor air pollutants such as NOx emitted from natural gas stoves. These are cooktop burners as well as ovens in homes. Again, work led by Eric Labelle, a student. He's shown on the right. And similarly, for a stove to the water heater figure, you want to understand, what's happening when the stove isn't being used. So what are the steady state off emissions? And in this case, you see trace here for methane on top, carbon dioxide in blue in the middle, and NOx gas in the light green. And you see that while the appliance is off, when we were measuring emissions in the kitchen, you don't see carbon dioxide or NOx increase at all through time, but you do see a slight increase in methane through time. That's our steady state off emission. Then the burner or the oven kicks on, you see a rapid rise in methane. That's the puff of methane into the air. Then there's a cycling of ovens in particular. It goes up to temperature and then cycles on and off. So we integrate all of these things into our estimate of emissions, the steady state off, the on-off pulses, and the uncombusted methane while the flame is actually on. I'll point you to some previous work. Brett Singer has done probably the most work in this area at LBNL. Mark Fisher also, and Zach and Paul in their paper from 2019 is worth a look too. There are 40 million US stoves that emit methane through leakage and incomplete combustion. And we found that stoves emit anywhere from 0.8 to 1.3% of the gas they use as unburned methane. That's really high. Now, stoves, in terms of total gas used, are smaller than both water heaters and especially furnaces. But nonetheless, the number was 0.4% for water heaters, 3 times higher than that in our estimate for stoves. So that's quite a high number, and there's a lot that we can do to reduce those numbers. And interestingly, for stoves, more than 3/4 of emissions occurred just simply while the stove was sitting there off. And that's that slow bleed of methane into the air that adds it up over many, many hours, over many, many days, multiplied by 40 million stoves in the US. So it's a steady state off emissions that dominated the methane to the atmosphere. For NOx, the results were different. NOx was formed only when the flame was on or burning. And we found that NOx emissions, as shown in the figure at the bottom, were linearly related to the amount of gas being burned at a time. That was true both for stoves and for burners. So you see NOx flow rate on the y-axis as a function of natural gas burn on the x-axis. Emissions averaged, as you can see, about 20 nanograms of NOx per therm of joule, per joule of gas burned. And that NOx is broken down into nitrogen dioxide and nitric oxide. Nitrogen dioxide is an irritant. It can trigger asthma, coughing, and wheezing. So it's the chemical species that's of most concern indoors of the NOx gases. We also found that families who don't use their range hoods and most don't. So only about a quarter of people in the US on average turn on their ventilation hood when they turn on their stove. So that's one recommendation to take home from today. Every time if you have a gas stove, every time you use it, literally every time, please turn the hood on. So families who don't use the range hoods, who have poor ventilation, we found can surpass the 1 hour national standard for NOx and nitrogen dioxide within a few minutes of stove usage, especially with smaller kitchens. So there are indoor air quality and health issues associated with indoor appliances, as well as climate issues. So interestingly, when our paper came out, the EPA, in this case, a spokesman, Tim Carroll, in an article in the Washington Post, acknowledged that the EPA don't include post-meter leak emissions in their estimates currently, such as these, especially uncombusted methane. So they're not included in the EPA inventory, but the EPA plans to do so in the coming year, starting in 2022. So we'll get a more complete picture of methane emissions to the atmosphere as part of their sort of downstream to upstream summary for the natural gas supply chain. Well, I want to end with a couple, I guess, sources of optimism, reasons for optimism. I referred to this a couple slides ago, the fact that there's a lot going on, a lot of exciting things happening with aircraft flights, especially with drones and satellites. So these, in a sense, especially for the latter two, satellites and drones, can be thought of as sort of almost automated ways to detect big sources. So many of you probably saw a paper that came out a few weeks ago, led in the Netherlands using the Tropomi satellite. And the paper in Science identified 700 sources around the world using the Tropomi data that were responsible from their calculations for 10% of fossil emissions. So if that's true and consistent, in a way it's bad news that there's a lot of methane going to the atmosphere, but it's good news if you can turn a wrench at 700 sites and reduce fossil emissions by 1/10. And so the question is, how quickly can we get those sources turned off? And then how steady are they? Is it like whack-a-mole where sources pop up and then disappear? But anyway, I'm really excited about the new satellites that are launching, the Carbon Mapper that Riley Duran's leading, and the Methane Sat from EDF. And the images that you see in the slide go back to Riley's work. Maybe some of you on this call. This was a paper from a couple of years ago in Nature, where they flew California over periods of time. And each of the plumes on the right you see is methane and hydrocarbons from individual point sources. These are oil and gas wells, landfills, wastewater treatment facilities. So again, this kind of technology will allow us to find super emitters, or the ultra emitters, as the LeBeau and colleagues called them in their paper. So once the satellites are in place, we have the ability to sort of scan the Earth almost in real time and find these. So I'm really excited about the new technologies that are being put into place. And I want to end with a few thoughts about restoration. So I believe that restoration should be our goal for the atmosphere, that temperature stabilizations of 1.5 and 2 and 3C are important. They're important for understanding consequences, but ultimately our goal should be to put the atmosphere back the way it was. And a definition for restoration in the ecological society is the practice and process of assisting the recovery of an ecosystem that's been degraded, damaged, or destroyed. And in my view, the atmosphere is no different than a wetland or an ecosystem. Our goal should be to put it back the way it was. And as an analogy, the Endangered Species Act mandates not just preservation of species, but actual recovery of those species to kind of self-replicating health. Pep Canadell and I wrote an article in Scientific American magazine a couple years ago, sort of proposing this notion of restoration recovery for methane in particular. And I think there's an opportunity for methane. And the reason I bring this up here, because for carbon dioxide, if you had a magic wand and could eliminate emissions today, there would still be 1 trillion plus tons of extra carbon dioxide in the air for centuries. But that isn't true for methane. If we had a magic wand that could eliminate or choke off all methane sources today, the atmosphere would go back essentially to normal within a decade or two. And so recovering and restoration for methane is something that is possible to see in the lifetime of some of the people on this call. And I think that should be our goal. And one additional tool to think about that I've been doing a lot of work on lately is trying to think about, can we remove methane industrially or biologically from the atmosphere after it's been released? So coupling this idea of methane removal and atmospheric restoration. This is a paper that we published in Nature Sustainability a couple of years ago. And then last fall, we published a couple of papers in the Phil Trans special feature that you and Nisbet organized, I referred to earlier. One of them was a roadmap or a research agenda for atmospheric methane removal. There are lots of different technologies in principle that we might do this by. None of them are easy. None of them will be cheap, but there are billions of dollars being spent on carbon dioxide removal, and I believe we should be looking at methane removal as well. But first and foremost, our goal should be to mitigate and eliminate methane emissions. Point you to some other papers. Sam Abernethy had a nice paper on the benefits of methane removal, not just for climate, but for reducing ozone concentrations near the surface and health. Renaud de Richter has been thinking about methane removal for a while. Renaud is based in France. And Desiree Plata there at MIT had a nice paper out just a month or so ago on using zeolites, as we had discussed in our 2019 paper, for oxidizing methane. So I'll point you to her paper in ACS Environment AU, the new ACS journal. So I want to stop there and open it up for questions. Thank you for listening. And I would say keep the faith, and we're all working to the same goal. So thank you for your attention.
Thank you so much, Rob. That was fantastic, and we appreciate the Boston specific samples, even if it's for bad news. Anyway, now we open a round of questions. So if you have questions, please raise your hands. First one is that I have here is, let's see if I can. Oops. Okay. Sorry. Okay, so Max. Oh no, that hand is no longer raised. I think Sersin, you had your hand raised.
That was an applause. Sorry.
Okay, yeah, it was.
People can use the chat too. I can monitor the chat
Yes.
now if you want to do that.
Yeah, exactly.
So just jump in, use the raise hand function or the chat, whichever you prefer, or just comment as well.
Yeah. So Rob, I have a question. So for CO2, it's pretty obvious that the way that terrestrial ecosystems sequester carbon dioxide is through photosynthesis, but how does it work for methane? That might be less obvious for people.
Yeah, no, it's a great question. There isn't an analog for methane in the way that there is for carbon, where plants don't, microbes consume a bit of, I guess the closest analogy from an ecology or an ecosystem perspective would be the role that microbes play. So microbes do remove or oxidize methane from the atmosphere, but the sink globally is pretty small. I showed it before. It's about 40 million tons a year. And this happens primarily in upland, what we call upland soils, drier conditions. So not the waterlogged conditions when microbes are generating methane, but there are microbes in unwaterlogged conditions that are essentially eating the methane, consuming the methane. So that's the closest thing to a natural source of removal from the atmosphere. There are people working with startups to try and use microbes or enhance microbial oxidation of methane in slurries by running high methane concentration gas over and through methane-rich microbial water, essentially. So you can try and enhance the microbial sink. So there's a lot of work in that area that's happening.
Okay, thank you. We have a question from Maya. Maya, I don't know if I pronounced your number correctly, but feel free to just pick up if you want, or Rob, you can just read the question.
I'll read it if Maya doesn't jump in. I'll let her
Okay.
go first.
So I guess my question was, I've been seeing, I think it was New York, where they said they're going to ban, natural gas and want new buildings to essentially use electricity. And if that is the trend forward, how does that impact emissions and especially methane, I guess, from gas cooking stoves?
Yeah, that's a great question, Maya. Thank you. You're right. New York City passed a moratorium on new natural gas hookups starting in, say, 2027. There are some exceptions, but it's for homes and buildings. And there are more than 50 cities and counties here in California that have passed similar bans. And the idea behind these is to think about the time to phase out appliances and infrastructure is when you're either replacing them or keeping them from being put on the ground to start with. So we don't want to take a brand new stove, we don't want to rip something out of someone's home if we can do it more cheaply to keep that stove from going in the first place. And these bans or moratoria are being put into place to say at some point in the future for climate, we have to stop using fossil fuels. And if we allow homes and buildings to lock in those emissions for many, many decades, it becomes almost impossible to do that. And it's not cost effective to then go back later and say, all right, get rid of those. So I do support these bans on future gas hookups. I think they make a lot of sense for climate and for health. I acknowledge I'm a little bit of a libertarian, so I don't really like bans in general. But in this case, I think phasing out natural gas hookups from new construction make a lot of sense. Let me add one more thing. There's another part to Maya's question, and that's obviously what the source of the electricity is and how clean that electricity is. And here in California, it's quite clean and getting cleaner all the time. I confess I don't remember what New York's mix of fuels for electricity is. But the idea behind them is that as we move forward, we need to move towards cleaner electricity. And as we clean up the electricity and the fuels and renewables that go into it, then these switches to electric appliances will make more and more sense. So you have to take a long view on those transformations. So I see a couple of other things. So Shiz, as we transition to electrifying appliances, buildings, it sounds like, well, I'm sorry, why don't you go ahead and ask? I'll just shut up. Do you want to ask your question?
Yes, hello, hey, can you hear me?
We can.
Okay, fantastic. So the question is, so as we transition to more appliances and buildings being electrified, like Maya just mentioned, I feel like I didn't understand the value of mitigating the leaks and how substantial that was. So, but then again, I'm not in the game. So at the folks that are actively working on electrifying some of these sectors, whether it's like in the private sectors or in the startup space or in ERE in the government, do you think that the impact or the size of that is well understood and a part of the value prop that's being used to progress some of these initiatives or these industries?
And maybe just a quick follow-up. Are you referring specifically to the methane emissions as, say, compared to the carbon dioxide emissions, which are much better known?
I'm sorry, I missed the first part of that question.
Are you referring to the methane emissions specifically?
Yeah, methane specifically.
Okay. Yeah, so I would say that we understand and have data on the methane emissions to a much poorer extent than we do for carbon dioxide emissions. The carbon dioxide estimates are pretty straightforward. You burn a certain amount of gas, you generate a certain amount, a predictable amount of carbon dioxide. So I think we have a good handle on that. But there have literally only been a handful of studies looking at methane emissions in buildings and homes and from appliances. And I referred to almost all of them in that list in my slide earlier in the talk. So I think we don't have a good handle yet on how much methane is being emitted to the atmosphere. And like happens pretty much everywhere that studies have looked in the last decade or so, whether it's upstream in oil and gas fields, distribution systems, and now here through our work and other people's work in homes, we keep finding emissions to be higher than they were expected to be. And that's been a pretty steady and predictable outcome from these these studies. So I think we've been underestimating methane emissions throughout the supply chain, and that's true for homes. I think we also haven't fully taken into account the benefits of electrifying for say indoor air pollution. It isn't just NOx. There are carbon dioxide gases generated, formaldehyde in small amounts. We're looking at other gases in particular. So I think if the ventilation is good in a home, the hood's on, working properly, especially with windows open, those issues aren't as likely to be as much of a health risk. But if you can imagine people in a prefabricated home, a trailer, people in poor communities will have smaller kitchens, perhaps poor ventilation equipment, and they're, I think, at greater risk for indoor air pollution. And so we can eliminate all of that by electrifying our homes. We can reduce the greenhouse gas emissions. We can clean up indoor air pollution that triggers asthma and other things. So I really view it as an opportunity for a win-win.
Okay, thank you.
Thank you, Rob. We have a couple more minutes, and we have James next.
Thanks for a wonderful presentation, and I enjoyed and learned quite a bit. What I'm curious about is what you think might be the 2 or 3 biggest policy challenges that you're dealing with now, and how do you go about pursuing those policy issues, questions, arrangements that you're seeking?
Yeah, great question. So I think there are a lot of policy issues around electrification. I really do think electrification is one of the biggest levers. The thing that's harder, in my opinion, about methane than carbon dioxide is how distributed the sources are. So again, most of my talk was about fossils because that's where we've done most of our work, but the largest sources are agricultural, and it's hard to think about how you eliminate methane emissions from 1.3 billion cattle on the planet, and relatively low level sources from rice paddies, from manure, digesters and issues like that. So I think we really have to address the agricultural sources of methane more than we have in the past. And there are policies being put into place, some in Europe, some here in California and elsewhere, that are starting to tackle that. But agricultural methane is hard. And frankly, it's easier for people to sort of point the finger at what they perceive as a big fossil fuel company than at farmers. But agriculture is the biggest source of methane. We must tackle it. And I think it has to be through demand side management, what we eat and how much we waste, as well as through technologies that reduce emissions at small point sources. And do you have any suggestions or thoughts on what we should do?
Well, I'm an educator, so I'm thinking education is an approach, but the challenges of interacting between this of the science interacting with the policy are major challenges that have to do with electorates and all kinds of political ramifications and issues. And I think certainly agriculture is center to that, because people are very, very concerned about agriculture being overmanaged by federal agencies. So the challenge is to create policies based on the science that we have in hand and that we've constructed are very great, and not many people understand how to make that happen or what the best processes are. I don't have any good ideas, but I do think that we have to admit that that's one of the fronts that we're dealing with here is, how to get policies that deal with both the supply chain, but also with public behavior and so forth. It's a complicated area, but it seems to me that a lot less time is being spent on that than may be needed based on what we know. And certainly I think methane is already sort of behind the curve a little bit in the public imagination, because a lot of people just think it's well, it's just the gas that I turn on and use for my heaters. So I'm not sure that we're publicly at a position where we can start developing the necessary policies that will bring about the changes that would offer some mitigation. Yeah.
Yeah, I think I agree with you. I think that's changing. A couple of things are changing. I mentioned the global methane pledge. I think methane really is finally starting to see some international attention. I'm optimistic about that. There are policy things we can do about the handshake from, say, the satellite data that I mentioned, and early detection of large sources and getting those squelched. So I think there are some things we have to think about there, and great opportunities in that. And I think, frankly, it's a hard sell to for people to understand that my hamburger matters, my steak matters, but they really do matter. And so I think in terms of education, on the demand side, that what we eat and how much food we waste really makes a big difference for methane and for carbon dioxide emissions. My hamburger affects not just methane emissions, but it affects deforestation and other things too. So, so points well taken.
Yeah.
Thank you, Rob. If we have one more minute, we had one more question from Lau. Are you still here, Lau?
Yeah. Thank you, Rob, for a great talk, and thank you, Cesar, for the broad invitation to attend this seminar. So at the very beginning, you showed quite striking contrast between the CO2 emissions and the methane emissions, especially during the pandemic, showing quite alarming trends in methane that are quite opposite to the ones on CO2. Do you have an explanation for that? Is that differences in demand, or how would you explain that?
Yeah, thanks. Nice to see you. Thanks for the question. Yeah, so we did not. So as part of the Global Carbon Project and work led by Corinne Le Carré, we published a couple of papers looking at how the pandemic reduced carbon dioxide emissions, and it reduced them substantially, like 5 to 7%, and almost 2 billion tons, which was a record decrease. But we didn't see that for methane, and frankly didn't expect that for methane, partly for the reasons that we've just been talking about. Methane emissions aren't dominated by large power plants and vehicle exhaust, things that were quieted, if you will, because of reduced economic activity during the COVID shutdowns. So, agriculture continued, fossil fuel use continued to some extent, but we didn't see the kind of drastic decrease in methane emissions, and didn't expect to that we did for carbon dioxide. And that's because of, carbon dioxide is dominated primarily from fossil fuel sources, and methane is dominated by ag and natural sources too. So I think that's mostly the reason.
Thanks.
Okay, so yes, yeah.
No, I was just going to say, if you were going to sign off, I just wanted to thank everyone for coming, and feel free to email me. It's just rob.jackson@stanford.edu, and thank you for listening.
Please join me on a big applause to Rob. Thank you so much for accepting the invitation. It's always a pleasure to see you, Rob. Appreciate it.
Thanks for your series, Cesar. This is a good series.
Thank you, Rob. All right.
Take care.
See you, everyone.